Okay guys, let's continue 3.4 and talk about some applications. So if they determine the end behavior of the following, we'll have some pictures. We could have some equations. Let's do it. If we're just looking at a picture, we can kind of just look and see what it's doing. It looks like it's going down on both sides. So as x goes to negative infinity, f of x goes to negative infinity. So as it left, going down. And as x goes to positive infinity on the right, f of x is still going to negative infinity because it's still going down on the right side. Now, if you have an equation, you look at the first term and you ignore the rest. The reason for this is at very large or small powers of x, the more times you're multiplying by it, the larger powers, they overpower everything else. Think about x to the fourth there and the 2x. Take like 1,000,000 to the fourth. 1,000,000 to the fourth is a 1 with 24 zeros. 2 times 1,000,000 is 2,000,000. There's no comparison. It's so much more powerful that it dictates everything that's happening. Now this is a is greater than 0 and this is even. So that means it's going to be like x squared. So x squared we know goes up on both sides. So as x goes to negative infinity, f of x goes up, so positive infinity. And as x goes to positive infinity on the right side, f of x goes to also positive infinity. What about negative x cubed? We have a negative a. A is less than 0, and that's odd. So it'll behave exactly like negative x cubed, which is what it is. You'll have as x goes to negative infinity, f of x goes to infinity. And as x goes to positive infinity, f of x should go to negative infinity. Because the negative will take x cubed, like 1,000,000 cubed is a very large number, but then it's a negative times that. So it's going to go down. Now let's put it all together. We can find the zeros of a polynomial by factoring, plot the intercepts, plot the y-intercept by plugging in 0, and use end behavior and multiplicity to sketch the graph. We can also use 3 version 2. So the second option is to use a test chart. This is what I'm going to suggest. It's never a bad idea to use a test chart to determine this. See what I mean? So you say find f of x equals 2x cubed plus 5x squared minus x minus 6 given 1 is a 0. So if 1 is a 0, I can factor it out to find the other zeros. 2, 5, negative 1, negative 6, 2. 2 times 1 is 2, so this is 7, 6, 0. So I know it factors into x minus 1 and 2x squared plus 7x plus 6. What are the factors here? Factors of 12 are 3 and 4. So it looks like this will be 2x plus 3 and x plus 2. When we factor it, I just skipped steps. You can write it out to figure those out. What are these? My zeros. This is x equals 1, x equals negative 3 halves, and x equals negative 2. Okay, so that means, okay, these are all zeros. 1, 0. Negative 3 halves, 0. Negative 2, 0. I can plot all of these. Negative 3 halves, 0, and negative 2, 0 are really close together. That's okay. And I can take them and put them on a test chart. Remember when we did positives and negatives in chapter 1? To see if it's positive or negative, we can use that to sketch. I know also when I plug in 0, I get negative 6. Because when I plug in 0 up here, the only thing that's left is the constant. So if I put these in order, negative 2, negative 3 halves, and 1, I can take numbers between them that are easy, 0, 2. There's not anything easy here, but we'll talk about it in a second. Negative 3, which is fine for us. Really, we could say what's between negative 1.5 and negative 2, maybe negative 1 3/4, which is negative 7/4. And we could plug it in or not. I sometimes find it easy to plug it into the factored form to see what's going to happen, and we'll see why here in a second. So what happens when I plug into negative 3? This is negative. Negative 3, this is negative 6, so this is times negative. And negative 3 plus 2 is a negative. So what's a negative times a negative times a negative? It's a negative. Now what does that tell me? It tells me all the numbers left of negative 2 are negative. That means coming out of this negative 2, I know I'm going down. Since this is a sketch, I'm not super concerned by exactly where it is, but it is important to know that it's going down. We already plugged in 0 and got negative 6, so we know these values are negative here. So it's going down, but we know if it's going down here, it's got to turn around to get back up to the 0 at 2, or at 1. Now if I plug in 2, 2 minus 1 is positive, 2 times 2 plus 3 is positive, and 2 plus 2 is positive. Positive times positive times positive is positive, so I know it's going up. The only question here is between negative 2 and negative 3 halves, is it positive or negative? Negative 7/4 minus 1 is negative. 2 times negative 7/4 is negative 7 halves. Negative 3 1/2 plus 3 is negative. And negative 1 3/4 plus 2 is positive. Negative times positive is positive. So we know it goes up. Probably not very much, though, because it's got to turn around almost immediately. And this is how you would sketch this graph. If it's already factored for you, the zeros are easy, but plugging in, you have to be more careful. I think in your homework, all you have to do for a polynomial, if it's like x to the cube, is you plot 4 points. Just like on a quadratic, you could plot 3 points. So let's talk about more theorems which can help you with things. The intermediate value theorem, if x is a polynomial with only real coefficients, and for real numbers a and b, f of a and f of b are opposite signs, and there must be one 0 between them. So this is something we talked about on 3.3. If they ask you to show something has a 0 between 2 and 3, you're going to do synthetic division using both of those numbers and show that the remainders are the opposite sign. 1, negative 2, negative 1, 1. If we use synthetic division, 1 times 2 is 2, 0, 0, negative 1, negative 2. So when you plug in 2, you get negative 1. When you plug in 3, you get 7. So if f of 2 is negative 1 and f of 3 is 7, that means somewhere between them, you're going to have to cross 0. So whenever there's opposite signs, there is a root between them. Now, the boundedness theorem is a little more complicated. If f of x is a polynomial with only real coefficients and positive coefficients in front of the largest degree term, f of x is divided by x minus k. It's kind of an extension of the Descartes' rule of signs. If k is greater than 0 and all numbers in the bottom line of your synthetic division are non-negative, it is an upper bound. If k is less than 0 and all numbers in the line of your synthetic division alternate, using 0 as positive or negative as needed, k is a lower bound. So it says show all roots are between negative 1 and 3. We need to show 3 is an upper bound. So negative 1 is lower. Let's put the 3 on the outside. 2, negative 5, 0, 3, 1, 2. 2 times 3 is 6, 1, 3, 3, 9, 12, 36, 37. So what they're saying here is these numbers are all positive, which means 3 is the upper bound. Now for lower bound, when you take the negative number, you need to alternate sign to be a lower bound. So 2 times negative 1 is negative 2. So this is negative 7, positive 7, negative 7 is negative 4, 4, 5. So these alternate sign. So it means lower bound. So if negative 1 is a lower bound and 3 is an upper bound, that means all the roots have to be between negative 1 and 3. This is useful when you have a lot of values to test and you want to rule out, like on the 3.3, those things with 180. If you had tested a number, you could rule out all the ones above it. And that's all for 3.4.